Well, welcome everybody. Good to be with you in Minnesota. It's actually still light out here in California and 75 degrees, but I hear you have snow. So I wish you'd send a little over here. We've had a lot of heat and smoke out here this year. Anyway, it's my great pleasure to give you an overview of the Cassini mission to Saturn. And I'm going to give you the story of its grand finale and all the things that led up to that. And this is my insider's perspective. I had a chance to work there at the famous jet propulsion laboratory in Pasadena. Here you see me standing under a half-size model of the thing that's at the California Science Center. And Cassini was the largest and most successful mission to the outer planets ever. Wanted to just mention that I worked with Dr. Henry Richter, who was a JPL pioneer, on a book. He was one of the early managers. In fact, he's the last surviving manager of Explorer 1, which you see at the top there. Let me see if I get my pointer here to work. Pointer options, there we go. Up here is the Explorer 1 model at JPL, and that's the mission where he helped design the communications link to Earth and back, and also the instrument package in the satellite that detected the Van Allen radiation belts, among many other things. So he's a famous astronomer and manager, and it was great fun to work with him on a book called Spacecraft Earth, a Guide for Passengers. So you can find this at Creation Ministries International. I recommend you read Richter's book, which I was glad to help him on. And so let's get into the story here. I was deeply embedded in the Cassini mission. I didn't work as a scientist, but I was the team lead system administrator. And that's a very complex and diverse job where you have to take care of the computers and the software for the ground systems, which are the computers that send the commands up and receive the commands down. We were also in charge of networks and just many different things that we had to do. So, but as you know, my ending there was not very happy. I was discriminated against for what they considered religious views, and my crime was sharing DVDs on intelligent design, particularly The Privileged Planet. How many of you have seen that movie from Illustra Media? I imagine a lot of you have. Beautiful film. It's non-religious, filled with science, and it has 4 JPL scientists in it. So I thought, well, this is fair game. They were filmed with NASA permission on the lab. So I thought, oh, okay, well, this is a nice way to just be an icebreaker and a conversation starter for people. And so I shared probably for a few dozen people that I knew, who I was friends with, and that got me into trouble. And so my story was told in World Magazine twice. The 2 films I mainly shared were Unlocking the Mystery of Life and The Privileged Planet. But as you know, academia and the scientific establishment are dead set against any criticisms of Darwinism. And so the moment they hear the C word, creationism, it's like a trigger that turns some of them into irrational bigots. And that was unfortunately my experience. If you're interested in the whole story, perhaps you've seen Jerry Bergman's trilogy here, the Slaughter of the Dissidents trilogy, where he details many stories of people who lost their jobs, were denied tenure, and many other bad things that happened to people who dared to question Darwin. And so I'm in volume 3 on the right side there, Censoring the Darwin Skeptics, chapter 17, gives you a 40-page synopsis of what happened in my case. Anyway, it was not all bad, just the ending was unhappy. But way back in 1996, when I first started working there, I brought my nieces, nephews, mom, and we wanted to see the real bird. So we went into the clean room and saw the real Cassini while it was being prepared before it was shipped to Cape Canaveral for launch. And now all of these are, my mom's in heaven now, but my nieces and nephews are all grown up and have lives of their own. But we actually did get to see, and it's a big machine off there in the corner, you see, covered with protective material to protect it from space radiation and debris. And here's how it looks. Big spacecraft, large high gain antenna on the top there. Uh, with that, they send the commands a billion miles back to the Earth from there. Actually, 880 million miles, I believe, is the closest distance from the Earth to Saturn. And so on the side, you see that gold-covered flying saucer. We're going to talk about that soon. That is the Huygens probe, a flying saucer that was going to land on the surface of Titan, the large moon of Saturn. And that was built by the European Space Agency. Let's get an introduction to this mission.
When I first started working on Cassini, my daughter Jennifer had just started kindergarten, and now she's married with a daughter of her own. I've worked on the Cassini project for almost 30 years, and that's an entire Saturn orbit. Part of Cassini's success is really the tremendous international collaboration.
We had 3 space agencies contributing to this: NASA from the United States, ESA, the European Space Agency, and Aerospatiale Italian, the Italian Space Agency, all contributing hardware to this mission.
The beauty of Cassini is the design. It's the largest outer planetary spacecraft ever built. 12 different instruments brought from all over the United States and Europe. The Huygens probe, built by the European Space Agency. When you put all of that together, it's just a monumental machine.
All right, Cassini by the numbers. Look at these numbers here. I'm not going to read all of these to you, but 2.5 million commands executed. Isn't it amazing how they can send commands, ones and zeros, across almost a billion miles of space and receive them back in antenna dishes? And you heard the speaker, they say the beauty of Cassini is the design. So they know about intelligent design, right? Anyway, 6 named moons discovered, 162 targeted flybys. In other words, those were intentional flybys of moons, including Titan and the other ones we'll talk about. There were 27 nations that participated. It traveled almost 5 billion miles in its nearly 20-year mission. And here's the science papers published. I think it's probably well over 4,000 by now. And almost 5,450,000 images taken. So very, very successful mission. Now here's a timeline of the mission from 1997 on the left to 2017 on the right. And the blue line here shows the time that I was on the mission. So before the launch in October of 1997, about 6 months before the launch, I started working on the mission. And then all the way past the primary mission, here's the arrival 2004, all the way past the prime mission, all the way past the first extended mission and into the second extended mission. So I was very fortunate to be a major part of this in the computer sense of this mission. And of course, things continued after I was laid off all the way to 2017. So it was a great privilege and honor to work there in the Jet Propulsion Laboratory in the Space Flight Operations Facility, very famous. Here you see some of our Cassini pictures along with some of the Voyager pictures that had been taken back in 1980, 1981. And I was in charge of a big Solaris servers and network machines, backup machines. We had a whole server room of things like this. I had to know a lot about them. And I was the team lead for 9 years of a group of five men and women who helped serve on the system administration team. Look here, I also had a white Saturn car, like my friend Dave Duty. We both had 2 Saturn license plates on me. So that was fun. I also enjoyed being an outreach speaker for Cassini, and I would go out to astronomy clubs like the Orange County astronomers you see here and speak to them about our accomplishments on Cassini. And I also led tours of JPL on the lab. Here you see a tour group in the center with the Bible Science Association we had, but I also led school groups. They would come on buses and I would take high school students around the lab and show them all the wonderful things and encourage them to consider careers in science. So I was well respected there for most of my time. I had a good time, a lot of friends. I loved working with people. My only fault was sharing intelligent design. Not my only fault, but that was my crime, was sharing DVDs on intelligent design with some people. Here's how many people worked on the mission at launch at the top and at the arrival at Saturn in 2004 at the bottom. And so you can prove that I was there, right? Well, let me help you out. Follow the bouncing ball, and there you can see that I'm among crowds of hundreds of people. I think over 300 people worked on the mission at JPL, but there were also many others, scientific teams across America and in Europe that I helped them with their computer needs. When they took an all plus alumni picture on the last legs of the mission, they had probably over 1,000 people, but I'm not in this picture because by that time I was persona non grata. I had been reprimanded, removed from my team lead position, yelled at by my boss, and threatened with a sword of Damocles over my head by a written reprimand for having shared these DVDs. And that was the reason. It was not because of bad work habits. It was not because of anything or incompetence on the job or anything like that. It was, and I can prove from emails that I got that that was the reason why I was reprimanded. So I started going through internal processes, the ombudsman, I tried to appeal the decision and no action. So I got in touch with Alliance Defending Freedom. This is just the short story. And they sent me an attorney who worked with me. And we said, look, this is wrong. If you don't correct this, we're going to sue. Well, they did nothing for 7 months. So we gave them plenty of time to mull it over. They didn't. So we issued a lawsuit. I was not fired immediately because that would have been retaliation, which is illegal. But they schemed and planned, how can we get rid of this guy without making it look like retaliation? Basically, they finally did. I was walked off the lab suddenly without warning on January 24th, 2011. So we had a lawsuit pending, but it was like a 3-year process to try to get justice. We finally got to trial in 2012. And after months after the trial, we went before a judge, not a jury. And he took months after the trial, 22 witnesses, 3 weeks, downtown Los Angeles, and didn't come to a decision until Halloween of 2012. And his tentative decision was, I lost on all counts. 10 counts, we thought we were going to win something. And he ruled against me and gave the whole case to JPL to write up. And so that was the official story in the newspapers. We actually had one more chance to try to contest it, but in January of 2013 was when we got the final decision, no change, and I lost the whole case. And that was widely published around the world that I was stubborn and a bad worker, and that was the story that was told about me. So my reputation was trashed, and I lost this opportunity. I was trying to ring the Liberty Bell, folks. I was trying to give religious freedom and freedom of speech at this prestigious lab. And the Lord had other plans. I want to just say that I'm very happy today. In fact, let me stop share so I can speak to you directly. I want to say that God compensates marvelously, and I'm very happy today. I'm having a wonderful life. God has given me many opportunities. I'm only making about 1/4 of what I was earning at JPL, but I have enough. I'm content, and God has been good since those days, even though they were days of trial. By the way, at that time, that month when I lost the case, I was also 10 days earlier diagnosed with cancer. My mother was dying, and so I got kind of a triple whammy that January. But I had surgery in late February, March, and the surgery was highly successful. It didn't remove all the cancer, but it's treatable. And look, here I am 7 years later, hiking, exploring, feeling great. So God is so good, and a lot of people were praying for me. All right, let's go back to the slides here. That's just the brief synopsis of what happened. Share again, here we go. So that was the last picture of the whole team. Will this slide advance? I hope. Come on, there we go. Now, who is Cassini and why was it named for him? Well, Cassini was an Italian astronomer who changed his Italian name, John Domenico to French, Jean-Dominique Cassini. He worked for the French Academy of Sciences in the 17th century, and he was the discoverer of the Cassini division, which you may have heard a gap in the rings. He also discovered 4 of the moons of Saturn: Iapetus, Rhea, Dione, and Tethys. And so it's appropriate that he was named for the main ship, and the flying saucer that flew to Titan was named for Christian Huygens, who was a Protestant and a Christian, as far as I can tell, important early physicist, and he's the one who discovered Titan. So for the mission to Titan, it's appropriate he was awarded the name. Here's how big it is. It's big as a school bus, huge machine, loaded for bear. Look at all the instruments on the right side. I'm not going to read all this, but you've got infrared instruments, you've got visible light instruments, you've got ultraviolet, composite infrared, you've got the main antenna, which does radar bouncing off of surfaces. You've got ion and neutral mass spectrometer there. You've got another infrared instrument. MIMI is the magnetospheric imaging instrument. And also it had a tin can that collected particles called the, with a mass spectrometer in it, CDA, and so that was able to collect material from the gas and the material around the spacecraft as it flew and on the way there. Here it is in the fairing on top of the Titan V rocket before launch. I mean, how do you protect a school bus sized spacecraft on top of a rocket? But they had that all figured out. And so after a couple of delays, we finally launched on October 15th, 1997. Beautiful launch at night. You should see the movies of this, flying up into this cloud. It lit up that cloud like a chandelier and then punched through it, and it was on its way. So what do you do for 7 years to get to Saturn? Well, you take a scenic ride. And so we looped around Venus twice, then by the Earth, and then by Jupiter years later, and then finally Saturn arrival. And that allowed us to get the gravity assist that we needed. Otherwise, you have to carry way too much fuel to fly that far. But with gravity assist, you kind of get an extra gravity boost. So we had a little fun singing group on Cassini called the Cassini Virtual Singers, and I joined that early on. And so we would sing popular tunes and put Cassini words to them. And so here's a little glimpse of the Cassini Virtual Singers as we passed by Venus the second time and then by the Earth in late 1999.
Twice around Venus and past the Earth, to Saturn's rings we go. The engine burns to guide our turns through dust and plasma flows. Slingshot past Jupiter, surfing craft will wink and wave hello, and sled the probe through methane snow as Saturn bound we go.
So we were a big hit. I'm sorry if that was a little too loud for you. I'll try to control that. But every time there was a special occasion, we would sing, and they had a lot of fun. Anyway, here are some of the buttons and badges that we would get at each of the milestones. We finally got to Jupiter on December 31st, 2000, and took these beautiful pictures. As you can see, the black dot there is the shadow of Io, the volcanic moon of Jupiter. And here we even got time-lapse movies of the cloud bands spinning around. So, but we still had 4 years to go, 3.5 years actually, to get to Saturn. So that was a long gap. And you say, well, what do you do all that time? Do you just sit there and eat lunch? No, they launched the machine without the flight software. So we were frantically going through upgrades of flight software on all the computers for years, and we finally had it done in time. And our first encounter was to the little moon Phoebe. Now, Phoebe is an oddball because it goes retrograde. It's the outermost moon of the Saturn system, and it goes opposite all of the other moons. It's only 130 miles across, and it's shedding materials that creates a ring around Saturn, we discovered. It's called the Phoebe ring, and that goes retrograde also. So how long could it be doing that? For billions of years? I doubt it. But anyway, on June 11th, 2004, we had our first and only close look at Phoebe. These are pictures at the bottom that Voyager had taken, but now let's see what Cassini's cameras can do. The best pictures ever taken of this small moon. I'll be showing this diagram from time to time that shows all of the moons of Saturn superimposed on a map of the United States. So you see their relative sizes. The big yellow disk is Titan, and then you have the medium-sized moons, and you have the Earth's moon in the lower right for comparison. And Phoebe is that little red one that's about the width of Florida. So we were all excited to watch the first images coming in. We had the NASA administrator there, we had a senator there, we had the JPL director, the Cassini manager, and various scientists, and the janitor off there to the right that you can see. And so here we go. Here's Phoebe from the Cassini cameras, and wow, what a surprise. You've got, it looks like it's dust covered, but the dust is pretty shallow. And as you can see, there are landslides where the dust would fall down maybe 12 miles off that cliff and expose freshwater ice. So here I am again with the scientists watching more pictures coming in from the Phoebe flyby, and we were very glad to see that the imaging system was working perfectly. I mean, look at the detail you can see. Here's a crater on Phoebe that's 8 miles across on this little moon. And down on the bottom, you can even see boulders down there. And so here I am standing by one of them to show the relative size. Okay, I'm just checking if you're awake here. All right, but here is mission control, just like in the movies at the time of the Phoebe flyby. And we still had a ways to go to get to Saturn. And one of the main events that had to happen just right at Saturn was the crossing site, as you see marked with X. And that's where the spacecraft had to hit just the right spot outside of the rings so that it could be captured by Saturn. And so we had an important burn to slow down the spacecraft at that point. And here's how it was going to come in on the sunlit side, and then the burn would happen for about 39 minutes, and then it would emerge from the backside. And if the burn completed correctly, then it would we would be captured in orbit and be on our way. So that was called Saturn orbit insertion on June 30th, 2004. And as you can see, the burn occurs backwards because it's trying to slow down the direction of motion. Here's another animation of the main engine burn. That main engine had not been used for years and it had to work. So we had a big event at the Pasadena Civic Auditorium where the Cassini virtual singers sang, and we were waiting for that burn to happen. And when it flatlined, everybody cheered and clapped, and we had a mission. If it had flown right by, that would have been the end of our jobs. So we're very happy. And the Cassini virtual singer sang again, and at that event.
It's the most wonderful time of the tour. With the payments of learning Cassini on our website and distract us from our
So happy days. You could probably see we graduated from transparencies to PowerPoint by that time. And I got the job of not only running the PowerPoints with little cute special effects there like that, but also arranging background tracks because I have a music studio here. So with my MIDI studio, I would write instrumental backgrounds that we could sing along with. So those were fun days. Okay, we had 4 main jobs on the mission once we were in orbit. Saturn, study Saturn itself, including its magnetosphere. The rings, obviously, is a big target, and all the icy moons of Saturn, the small ones, and then Titan, which is in a class by itself. The only moon with a substantial atmosphere. That was a big part of our mission.
turned the Cassini cameras down to look at the rings, revealing them in a way we had never seen them before. I remember coming back to JPL early in the morning just so I could be there and watch those pictures one by one come down. And I felt like I could almost reach out and touch the rings that were right there. We basically tried to carry in our toolbox everything you could think of to explore the Saturn system.
I joined Dr. Linda Spilker there. She was a Voyager scientist back in the Voyager days, and she became eventually the science lead for the mission. So I got up early in the morning to get down to the lab and see these first pictures come in, these unprocessed pictures, and these were being broadcast on TV as they were coming in. And we were just blown away by these, even though these were rough images that needed to be cleaned up of artifacts, we began to see tremendous detail in the rings, including waves like these. The wave at the lower left is called a spiral density wave, and that's a longitudinal wave that happens from Saturn itself. And it's kind of like sound waves that are longitudinal to the direction of motion. The upper one is a bending wave, which is caused by the outer moons waving up and down. And so those two things travel in different directions and cancel out in the middle in this noise here. So that was the closest, first time we had ever seen such a thing. It was predicted by the laws of physics, and this is physics in action here. Now, one thing you need to remember is that there's a difference between the front lit and backlit images here. If you look carefully at the Cassini division, it's dark when it's front lit, and the B ring is the brightest because it's the thickest ring, and it's mostly water ice, and so it reflects off of the surface. But in backlit light, everything reverses pretty much. The A ring stays about the same because it's basically medium density. But the Cassini division has dust in it, and that dust reflects like dust on your windshield, and so it turns bright. And then the B ring, since it's so dense, blocks the light, so it turns dark. And we saw other waves here inside the Cassini division. You can see there are a couple of ringlets right embedded inside. Another thing we witnessed that day was the F ring, a thin outer ring, which had been discovered by this man, Larry Esposito of the University of Colorado from Voyager, or actually Pioneer images before Voyager. So when Cassini got there, he was sitting there close, staring at it, and I recorded this picture of him enjoying his ring from Cassini, the first images he had. You know, many times I was the only one with a camera at these milestones taking pictures of things, and that surprised me a little bit, but I have a number of historic shots of these images. The F ring is shown in great detail here, and as you can see, this little moon Prometheus pulls on material toward the A ring here at each time it goes around. And there's another moon on the other side that pulls it away from Saturn. These are called shepherd moons, and they're like shepherd dogs, and they keep the ring particles confined to a very thin line there. Prometheus is important because it figures into the privileged planet hypothesis. If you remember the film and the book by that name by Guillermo Gonzalez, he talks a lot about total solar eclipses. And what are the conditions for getting a perfect match like we have on the Earth? So he decided to look around the whole solar system and find every instance where one body could eclipse another to perfectly match and cause a solar eclipse. To do that, all these combinations, about 60 of them, any of them that could do that would have to fall on this line, this vertical line. And as you can see, there are only 2 objects in the whole solar system capable of doing that. Earth's moon, which is right in the center of that line, and then this little moon Prometheus just touches the edge of that line. And so there were actually 2 cases that he found that could be, I'm going to move this wire, sorry about that. 2 cases where you could get a total solar eclipse. So presumably if you were in the cloud tops of Saturn in some kind of gondola or something, and if Prometheus passed by at just the right time, you might get a half-second total solar eclipse, was what he decided. Well, Cassini got there and found out that Prometheus is potato shaped, so you wouldn't get a complete coverage. And so the only body that we know in the solar system that has perfect solar eclipses is the Earth, which also has intelligent people able to appreciate and learn from it. If you've watched the film, you know we learned a great deal of science because of that coincidence that they call. All right, so here's Prometheus again, and you can see these, each time it goes around, it draws material out. These are called gowers, and you can see how several past flybys drew out material, but the other moon outside called Pandora is pulling them back in line, keeping them confined. Now, this is an interesting short animation I'm going to show you of the ring plane crossing, and what you're going to see is how thin the rings are. So let's start it. And as we go around, you can see the bright B ring, and you can see the A ring. The Cassini division is dark. You'll see moons going around, and watch how thin as we cross the line. Okay, here comes Titan. There's the F ring. Here we go. Boom. Now the brightnesses are reversed. Now the Cassini division is bright and the B ring is dark. And so they say that if you had the rings compressed down to the size of a football field, the ring plane would be as thin as a sheet of paper. Now that's all the laws of physics. This is Newtonian physics that orbiting bodies around a body because of gravity tend to squash down to the equatorial plane and get very thin. But there is some vertical structure on the rings as well. Anyway, what beautiful things. We started getting beautiful detailed black and white, but also color images of the rings. And with ultraviolet and infrared, you can even get more detail and learn about the composition of the rings. Like they're mostly water ice. They're exceptionally clean, which was a surprise to the scientists because after 4.5 billion years of meteoroids coming in and dust, you'd expect them to get very dirty. But as you can see, they're mostly water ice. And so that's a big puzzle. And the ring scientists who know about this stuff are quite surprised, and they cannot explain how these remain this white, this clean for billions of years. I mean, maybe 1 billion at the most. So I read the science articles on that with great interest. Another way to look at the rings is with radio occultation. In other words, you watch a star behind the rings as the star moves across the rings and you measure the brightness fluctuations. You can learn quite a bit. So they took this image on the bottom here. The top is visible light. The bottom shows more detail in radio signals. They take that curve and they stretch it into an image of a ring, and you can see, you can get a lot more detail. So look at the detail in the A ring, the B ring, but we didn't see any spokes. You remember that Voyager saw radial phenomena coming across the rings, and quite surprised by that. So we didn't see any for the first 3 years. It took several years before we began to see these radial features. Finally, in 2007, they started appearing. So it appears that these rings, these spokes, are material that are a function of the angle of the angle of sunlight that impinges on the rings. We started out with the rings pretty wide open as we moved toward equinox when the sunlight hit them on edge, and at a certain angle they started appearing. They think what's happening is material gets electrically charged and levitates above the ring plane, and as the particles orbit, they smear out. So that's what's happening there. Now, I like this image here because this is one we never get from the Earth. This is a backlit image. We're always on the front-lit side of Saturn, being an interior planet, but here's the shadow cast across the rings. Okay, time to look at some of the moons, and Titan is the big one. As you see, it covers the whole United States pretty much, and it was a primary target for Cassini and the Huygens probe. This shows you some planets and moons, large bodies of the solar system, so that you can appreciate how big Titan is. Here we have the Earth and Venus and Mars. So you got 3 planets, then Ganymede, which is the large moon of Jupiter, and that's larger than Titan, but not by much. And Titan is bigger than Mercury, bigger than a planet. So how can that be? Well, moons go around planets and planets go around the sun. So it's just an academic taxonomic type of matter. But Titan is certainly a special one, and it's the only moon in the solar system with a substantial atmosphere. In fact, it has 1.5 the density of Earth's atmosphere on the surface. So mostly nitrogen with a mixture of methane and other gases. Here were Voyager's best views of Titan. I remember back in the Voyager days that scientists were so flustered because they couldn't see the surface. There was the atmosphere got smoggy with a methane haze, and they just couldn't see down to the surface. So Cassini came prepared for that. Our first good look at Titan came right after SOI, Saturn orbit insertion. We have ringmasters like Larry Esposito, Jeff Cuzzy, and others who know a lot about this. We have the Huygens team managers there, and I was glad to work with all of them on their computers, help them out. So here we are again. I'm the only one taking pictures in this occasion, seeing the first images of Saturn come in. I might just mention that the Martians get all excited. The ones on the Mars missions, they jump up and down and they slap each other in the back and they get so happy when the images come in. And the Saturnians, they just kind of sit there and go, very interesting. So that was not surprised for that, but it was fun to see these come in. So as you can see, we're seeing structure down on the surface, dark and light areas. And what are those bright things on the bottom? They didn't know at first, but it turns out they're clouds at the South Pole. And that looks almost like a continent. So they were very excited to see more and more detail with more imaging. Sure enough, those clouds would move around. And so Titan has weather. It has a weather system. That's pretty exciting. With infrared mapping, we could see right through the haze all the way down to the surface. We had two instruments able to use infrared light to map the surface. We also had the ion and neutral mass spectrometer, which could sniff molecules in the atmosphere and determine what it was. So you see nitrogen and methane at the bottom, but we also found ethane and diacetylene, benzene, and a whole spectrum, a whole zoo of hydrocarbons and nitriles, which have nitrogen in them, that were being formed in the atmosphere in smaller amounts. Now, this is important because Titan spends up to 20% of its time outside Saturn's protective magnetic field. The solar wind erodes the upper layers of atmospheric methane. And so 20% of the time, Titan is exposed to the solar wind. It's beating on the atmosphere. It's stripping away molecules, and especially the methane. So over 4.5 billion years, why is there any methane still there? Anyway, the Cassini radar, using the high gain antenna, was able to bounce pulses off the surface and receive them back and build up maps over time of the surface. And so here's the first Titan radar map that we got in 2004, shortly after we got into orbit. And you see light and dark areas that they seem to resemble river channels or dunes or something going on down there. So what are we looking at? Well, the bright areas are rough and the dark areas are smooth to radar pulses. And so you can colorize that and get an idea, but they didn't know at first what they're looking at. Is this fluid flow? Is it wind? Is it perhaps lava flows from cryovolcanism? That's not hot lava, but cold lava, cold fluid material flowing out of vents in the surface. We found that the altimetry is remarkably flat. Using the radar bounces, we could determine the altimetry. And most of the surface of Titan only varies by about 300 feet up or down of the average. We did find some mountains up to 2,600 feet high, but for the most part, Titan is pretty flat. Here's the best volcano candidate for a vent where cryovolcanic material may be erupting out. But we also found the weather would change within months. And then we found very few impact craters. Now here's the biggest one we know of, called Circus Maximus. It's almost 300 miles across. And on the edge, you can see what appear to be river channels flowing into the crater, which is exciting because what this means is that the weather systems on Titan actually produce cloud bursts heavy enough to cause river flow, fluid flow across the surface. Here's a young impact crater with the surrounding ejecta blanket, and where it's located on Titan is right there. And you can see that they call that a young crater. That's a whole subject about crater count dating and young and old craters. But anyway, another surprise was that we found sand dunes. At first, they wondered, what are we looking at here? They look like cat scratches on the surface, but it turns out they're like the dunes of the Namib Desert in Africa here, longitudinal parallel dunes. So we learned that these dunes are about 2 miles apart, about 100 to 300 feet high, and they go for hundreds of miles. And you can see that they will flow around higher objects like hills. But that was a huge surprise. They didn't expect that at all. It covers 40% of the equatorial tropical latitudes. And what are the dunes made of? Mostly ice particles coated with organics that fall to the surface. We also found that Titan has lakes of hydrocarbons. And so we found them. Here's one at the top on the South Pole that looks like Lake Superior a little bit. So they called it that. But surprisingly, most of the lakes are at the poles, not at the equator. That's where the sand dunes are. So here's a radar map colorized to show some of the lakes at the North Pole. And they believe that there is more hydrocarbons, more oil, so to speak, on Titan in these lakes than all the Earth combined, all the Earth's oil deposits combined. So maybe they have cheap gas on Titan, I suppose. But anyway, here's Lake Ontario on the South Pole. It's like America's Great Lakes, and it's evaporating quickly. In fact, they presume that these, as the weather changes over 30 years from summer to winter, and the different poles, experience their summertime or their wintertime, that the hydrocarbons evaporate and move to the other pole. All right, here are some radar maps put on top of the infrared maps. And so by combining different instruments, you can learn a lot about a surface. Finally, we saw the landing site for the Huygens probe. That's where we were going to try to land that flying saucer built by the Europeans. Here's a picture of the Huygens probe, a model that was built by the European Space Agency. And you can see how it looks compared to some engineers putting it together in Europe. And the actual probe is the brass colored thing here with a big heat shield over it. And so it also was loaded for bear with instruments. I'm not going to read all these words to you, but basically it could study the atmosphere, the structure, it could study the wind, it could study the contents of the atmosphere on the way down and the aerosols. And then it had a lamp to illuminate the surface on the way down, and a surface science package. And they made this thing where they didn't know if it was going to land on liquid or fluid. And so they made it where it could land on either. Now here's Jean-Pierre Le Breton, who's the chief scientist for the Huygens mission. And I was fascinated listening to him present ahead of time what they were trying to do, what they're going to accomplish. And I remember thinking, wow, if they can pull that off, that will be a series of lucky breaks, because everything had to work like clockwork on time from a billion miles away with commands from the Earth that were stored on the probe ahead of time. And they had a major problem years before it landed with the communications didn't match. The transmitter and the receiver on the mothership, because of Doppler shift, didn't match, and they couldn't fix it in software. So they had to redesign the orbits to get rid of the Doppler shift so that the communication link worked. And they did it, and it worked. So the probe release was on Christmas Eve 2004. We all wore Santa hats to see that it worked properly. Explosive bolts fired and sent the probe flying free at just the right time, just the right orientation, and it was on its way. These are artist renditions, but these are actual images on the bottom right of the photographs of the Huygens probe from the mothership. So it hits the atmosphere, the top of the clouds at Mach 2, twice the speed of sound, and the heat shield heats up to 21,000 degrees Fahrenheit. That's over twice the temperature of the sun's surface. So that heat shield had to be well designed to take on the heat. Then after it cooled down enough and slowed down enough, parachutes would deploy, the first one slowing it down more, then another drogue parachute that would carry it down through the atmosphere for about 2.5 hours until it lands on the surface. So the artists ahead of time went crazy with drawings, images, paintings of what they were hoping to see. There's the lamp turning on just about 100 feet above the surface, trying to measure surface properties. There's one of the parachutes, the last one. And so what would Huygens find? This was going to be a wonderfully exciting mystery to solve. And they wondered, would it splash, would it splat, or would it thud? In other words, would it land on liquid or solid? And they built it to where it could do either. So here's an alien surface under an atmosphere with a weather system that was never before seen. Would there be lakes of liquid ethane or methane? That's what they expected. In fact, here's a picture of methane, CH4 on the top left. And as it's hit by the solar wind, it ionizes into CH3 ionized molecules that recombine primarily into ethane, which is C2H6. Now they know this happens, and so ethane has nowhere to go but down, and it won't evaporate or go back out again or turn into methane again. So it should accumulate on the surface. Here's what they were thinking. One can calculate how much ethane, there's ethane on the top right, has been produced on Titan over the entire history of the solar system. You remember, you see the assumption there, 4.5 billion years. The result is that this remarkable moon could be covered by a global ocean of ethane with an average depth of up to several kilometers. That was what was believed in 1999. Now, before we got there, we understood from Hubble images and other earthbound sources that we could see some structure on the surface. And so we knew it wasn't entirely an ocean. But still, artists thought that there would be a lot of liquid down there because this is supposed to be an ongoing billions of year process. So most of the artwork showed the probe landing on liquid with maybe some continents. And I remember on the night before probe descent, January 14th, 2005, they had a special event at the nearby hotel where they invited NASA officials and movie actors from Star Trek. And there's John Rhys Davies, actor, Lord of the Rings. There's Bill Nye, the science guy, always getting into something. And each one of these guys was very reluctant to predict what they were going to see. But the next morning, the big day arrives. There's Jean-Pierre at the top right, and there's some of his scientists. Look at the expressions on their face. They're really eager to see what's going to see. I'm going to show you, the real Titan in a moment, but I want you to hear this sound effect of, let me turn the pointer off here. Sorry. I'm going to start this a little ways in and turn the volume down to a comfortable level. But what you're going to hear are radar echoes off the surface. In other words, a pulse goes down, comes back up, and they get closer and closer together the closer to the surface it gets. And so the frequency goes up. And let's see if how it sounds on the way down. It's kind of fun. I always get a kick out of that. So let's see what the Huygens probe hit. On the way down, you can see that they got below the haze, and you can start to see what look like mountains and maybe river channels. And this almost looks like the coast of California. This is an unprocessed image, but pretty soon they got really good images. And so here's what they saw. It's down there on that dot was the landing site from orbit. And here's the first view from the surface. You ready? Well, maybe not really, but but here we go. I'm going to turn the volume down a little bit here. There are captions along with the music. I'll read the captions so that you can focus on the imagery. Years after the landing, they put together all of the images into a colorized movie of the whole descent. And at a certain point, you'll see actual images stitched together as if you were writing down on the probe to see what the probe was seeing. The European Huygens space probe rode piggyback to Saturn on NASA's Cassini spacecraft. Huygens' mission: explore Saturn's hazy moon Titan. On January 14th, 2005, Huygens descended to the surface. Here it hits the top of the atmosphere. And now this is actual imagery. Huygens cameras recorded the 2.5-hour descent. Titan's dense haze began to clear about 45 miles above the surface, revealing bright highlands of rugged ice and dark lowlands resembling a dry lake bed. Scientists were astonished to see dark branching drainage channels, indicating that rushing rivers of methane had flowed on the surface. Researchers had thought Titan might have a global ocean of liquid hydrocarbons. So Huygens was designed to float, just in case. Cassini later showed us that large lakes and seas are confined to the poles. Okay, we're coming in now, watch. Here comes the landing on that dot. And now there's the first view of the surface. The probe came to rest in the dark floodplain amid rounded rocks of water ice. And there's the light from the lamp, even caught a glimpse of its parachute's shadow. See the shadow there? Here's a reenactment. The descent to Titan represents a major milestone in the exploration of our solar system. Bounced a little bit, there's the parachute landing. No other spacecraft has landed farther from the sun. So that was exciting. The first view from the surface looked like this and colorized with what they expect the wavelength of light was at the surface. You see these rounded boulders are about football size, excuse me. And so you compared to the horizon on the moon at the right, you can get an idea of the size of things. So these are not very big, but they have rounded edges, which indicates that they tumbled down those river channels and flowed out onto the floodplains. So activity on the surface of an alien world, that's really exciting. But let's talk about that missing ethane. You know, it's supposed to build up over 4.5 billion years. After the landing, Jonathan Lunine, who's a astrobiologist and an expert on Titan, materialist, evolutionist, of course, he was baffled. Here's what he said. Since this chemistry is irreversible, we can say that products like ethane are being made and deposited on its surface. Now watch, if the chemistry on Titan has gone on in steady state over the age of the solar system, then we would predict that a layer of ethane 300 to 600 meters thick should be deposited on the surface. Well, how much was found? Zilch. That's a technical term meaning very little. And you know, I actually made a prediction before the landing that they would find maybe a little bit of moisture, but not much. And so my prediction was right. I got fired. His prediction was wrong, and he's famous. Anyway, justice. Atmospheric collapse. That's not the only problem. The methane acts like a space blanket. It provides some global warming on Titan. It keeps the nitrogen warm enough so that it remains in the gaseous state. But the methane, remember, is being eroded by ultraviolet light from the sun. And when the methane is gone, the nitrogen will freeze out and the atmosphere would collapse, catastrophically taking everything down with it. I learned this at lunch talking to some of the scientists, including Dr. Sushil Atreya, who was the chief scientist for the Galileo probe, which went into the atmosphere of Jupiter. He gave it an upper limit of 100 million years for this to happen. So, you know, 100 million years, that sounds like a long time. Sometimes, let me just quickly let you see my gestures here. Sometimes when I'm giving this presentation live, I'll stretch out a 45-foot rope on stage. And I'll say, okay, this rope represents 4.5 billion years. And I'll say, how much is 100 million years on this rope? And it's 1 foot, you know, just one little foot on the far right end. So I'm asking, what was going on the other 44 feet on this rope? Did it even exist? And yet they won't consider any difference from that. And so I was talking with Dr. Atreya, and he had no answer for why it's still there. So they have to do some serious theory rescue devices to try to keep their precious billions of years. All right, let's see if we can get the next slide here. There we go. Here are some maps of Titan taken in infrared imagery. Beautiful pictures there. We had a big celebration at JPL after the Huygens probe. Went to the Athenaeum at Caltech where Einstein used to walk, and it was a great time to celebrate our achievement. Now here is a diagram of Saturn, the limb of Saturn on the bottom with the moons. And you see there's a lot of small, irregular, icy moons, some small moons outside the rings, a set of medium-sized moons, and Titan, of course, all by itself. Then you have Hyperion, Iapetus, and we saw Phoebe already. But the rings, in comparison to the moons, here are the main rings down here that we see. Let me get to the pointer so you can perhaps see it there. These are the main rings we see from the Earth that were discovered centuries ago by Galileo. But this broad ring here is called the E ring. And we're going to talk about that a little bit because that's important. And as you can see, the moons stretch out all the way out to Phoebe. Here are the moons of the solar system scaled to Earth's moon. Here's Earth's moon here. Here's the Earth. And we go out, Mercury and Venus do not have any moons, which is surprising. Mars has 2 little specks that go around it. And Jupiter has 4 big ones and a lot of small ones. These are the Galilean satellites that Galileo discovered. Saturn has, I think the current count is about 62 moons. And Titan, of course, the big one, and a lot of smaller ones. We'll see a couple more of these, not all of them, in tonight's presentation. Uranus has about 6. Neptune has Triton, a very important moon. And Pluto has a big one called Charon. And that was discovered and explored in the last few years by the New Horizons spacecraft. Here's a storm on Saturn. So we were glad to see atmospheric phenomena, saw a lot of big storms. As you can see, the ring shadow is starting to get narrow because we're working toward equinox. This was on 2010. And we got to look at the North Pole and the South Pole. The South Pole has a hurricane big enough to swallow the Earth. And the North Pole has a hexagon-shaped storm, which is still somewhat of a mystery. So I read a paper just recently trying to explain how you get a hexagon. Here's part of the hexagon up here. And you can see inside and outside, there's a lot of numerous small cyclones, storms. So here's a top-down projection of the hexagon. It must be some kind of permanent standing wave, perhaps, that just finds a way to remain stable over many years. It's interesting that the hexagon matches the position of the northern lights, the aurora on Saturn. So a big mystery that has to be solved. We also studied the magnetosphere, a huge magnetic sphere of influence. And the Saturn is way down here embedded in this donut torus called. And the important thing to remember about Saturn's magnetic field, which is a very complex subject for, for PhDs with a lot of training, is that it doesn't match theory. The theory says that to get a dynamo effect that produces what they think is the way they produce a magnetic field, you've got to have a mismatch between the spin axis and the magnetic field axis. And that's what churns up the interior and produces a magnetic field. Well, sad to say, the spin axis on Saturn matches its magnetic field axis within, I think, 0.5%, like 0.1%. So it defies theory, and they don't have any answer for that. Okay, I'm excited to share with you the story of Enceladus, this little moon. It's about the width of Iowa there, or Arizona, if you please. This was one of the big surprises of the mission. Uh, Enceladus was revisited in 2005. It's the brightest object in the solar system. It's only about 300 miles across, but it reflects almost all the light that strikes it. Why is that? And so there it is compared to the British Isles. You can get the relative size of it. This was Voyager's best image of Enceladus. And already you can see something strange is going on here. You've got this heavily cratered northern hemisphere, but you've got this flow going through it that cuts off some of the craters in half. And many of these craters almost look like melted ice cream, you know, just sort of relaxing into the surface. And there's almost no craters on the southern hemisphere. And so for years, scientists have been wondering what is happening down there. Would we find ice geysers coming out of vents somehow? So Cassini was very keen to study this little moon and find out the secret. So we started looking for eruptions right away. Is this a plume down there? They weren't quite sure. This over here is Saturn shine. You've heard of Earthshine, maybe around new moon. You can see the dark side of the moon from reflected light off the Earth hitting the moon and coming back. Well, this is Saturn light hitting Enceladus and reflecting back to the camera. All right, on March 9th, 2005, we got even closer looking for plumes of material. We got great images of the surface. And wow, look at the detail here. You've got craters that look like they're relaxing into the surface somehow. And you've got cracks going this way and that, crossing other cracks. You can get an idea of the relative timing of things. Like if you see a crack going through a crater, you know that the crater formed first and then the crack went through it. But you can't tell absolute times from this. Now, Enceladus is made of almost pure water ice. There's no ammonia, no carbon dioxide, and those are needed to kind of raise the temperature of water so that the surface can melt. Finally, we got an extreme close-up in 4 months later, and we found what are called the tiger stripes. Look at these parallel cracks on the southern hemisphere. Some of them seem to branch into a Y shape at one end. Some of them have a curl at one end. What on earth is going on there? Here you see the heavily cratered northern hemisphere, but the very smooth southern hemisphere with these tiger stripes. And more details showed that they're located right smack on the south pole of Enceladus. So let's get going for a closer look. What do you say? First of all, we found out that the tiger stripes are the warmest part of the moon. There's heat coming out of these tiger stripes. Interesting. Now, not a lot of heat because it's relative heat. With the infrared, we're able to see the hottest parts are right in the centers of these cracks. And now look, 190 K, minus 120 degrees Fahrenheit. Boy, aren't you burning up from there? So it's very cold to Earthlings, but that's a lot warmer than the minus 300 degrees elsewhere on the moon. So it's significantly warmer in those cracks. Finally, we found plumes. 4 months later, we could see eruptive material coming out of those cracks. And that got really exciting, really fast, because we wanted to see these eruptions going on. They determined that the material is coming out very fast, and there's a lot of it, 120 to 180 kilograms per second are coming out of these cracks. In fact, we saw a surge of material coming out of Enceladus on the way into Saturn orbit insertion. The speed is about 400 meters per second of this material. Some of it erupts and falls back on ballistic paths onto Enceladus, but a lot of it shoots out past escape velocity. And so we found that there's so much heat coming out of these cracks. Here's what they expected, and here's what they later observed. 2.6 times the power output of all the hot springs of Yellowstone. Now, I was just at Yellowstone watching all the steam everywhere, and that's pretty amazing that you have that much energy coming out of a small moon of Saturn. Here's more plume images. It seems like no matter where it's positioned, you can see that this material is just spewing out rapidly out of Enceladus. And they determined for sure that Enceladus is the source of the E ring. This little moon creates a whole ring around Saturn, that big broad ring that we saw earlier. So Enceladus joins the Active Body Club. That's a very exclusive club with only 4 members. The Earth, we have volcanoes. Io is the most volcanically active body in the solar system, and Triton has nitrogen geysers out there at Neptune. So Enceladus, but look how small this moon is. There it is, that little dot there compared to the rings. And that's putting out all this material. And look how small it is compared to the other members of the Active Body Club. How can that happen? How can that go on for billions of years? That's the question we should be asking. All right. The backlit mosaic. Now this is a famous picture, and I'll tie it into Enceladus in a moment. But here you see a scene of Saturn that we never see from the Earth, because we always see the other side that's illuminated by the sun. But the sunlight coming through the rings lights up the rings like a chandelier, and it's just beautiful. Let me brighten it up a little bit so you can see better. And we're going to zoom in on the left part a little bit. And here you see Enceladus over here in the thickest part of the E-ring, spewing out that material, creating that ring. But what's this little dot over here? Well, ladies and gentlemen, that's you. That's the Earth from a billion miles away. And in fact, if you blow up that pixel a little bit, you can see the moon peeking out behind it. So what a dramatic image that was. Made National Geographic's Image of the Year cover story. So we're very excited to see things never seen by humans before. They took another image like it years later, and in this one they caught Mars and Venus and the Earth and Moon here, and still you see Enceladus over there pumping out that material. So here's the Earth image as seen from the later one. I remember on that day, when they were going to take that picture, they told all the people they could spread the word to on Earth to wave to the camera so they could get their selfie. But anyway, the plume sources were later reconciled with the tiger stripes in particular spots. And so those circles indicate where they knew that plume material was spewing out like geysers out of those cracks. And then we dove in for closer looks. This is an artist's conception of what it might look like if you were standing on the surface of Enceladus watching this material charging out of those cracks. So we started doing flybys of Enceladus at closer and closer ranges. I'm not going to spend a lot of time on these images, but just try to think of one thing is how you could fly a machine like this 1 billion miles away, so close to a small moon 300 miles across accurately, and get images of it while you're moving fast. And then just pay attention to the tremendous resolution detail that they got in these images. So here was a skeet shoot, they called it, where these are the footprints of the images they were hoping to take at high speed. And the first images came in August 12, 2008. Again, I'm the only one taking these pictures here. It was exciting to be there with the scientists and engineers watching these images come in. And here they are coming in with great resolution detail. Look at, you can even see boulders down there and such detail. So that was the first image. Now we're looking right down a tiger stripe down here, right across it. So fantastic images. Wow. Clear view down a tiger stripe at 98 feet per pixel. And you can see that material appears to pile up on both sides of the crack. That's because some of it falls back on both sides, while in the center it goes straight out. So here's they put the images together to create a puzzle-like appearance of what they're looking at. And wow, more circles where they know material is coming out. You can't see it from this angle, from this illumination, but material is charging out of those cracks. There's the outbound mosaic. They did another deep plume run. So here are some of the flybys of Enceladus over the years. They even flew right through the plume a couple of times so they could sample the particles. They found it's mostly water ice with a small fraction of sodium salts. So they figure there's an underground ocean somehow that is promoting this material coming out. They named the cracks Damascus, Baghdad, Cairo, gave them Near Eastern names. But more high resolution of these cracks, just amazing what they pulled off. Here's an artist's conception of what it probably looks like. And so that was exciting, Enceladus. And it's a great topic for young Earth creationists to study and say, how could this little moon be pumping out so much material for billions of years? More images, there we go. Okay, Dione, real quickly, just to show you some of the medium-sized moons, very high resolution detail. Rhea looks like it might have evidence for a collapsed ring. Maybe one time there was a ring going around it and it fell to the surface and created these deposits. Real quickly, Hyperion is a strange one. It's oblong. Here was Voyager's best image, and here was Cassini's best image. Deep craters with dark material on the bottom. And Hyperion tumbles around in a chaotic orbit, so that's a strange one. But the one more quick story is about Iapetus. This is one of the outer moons, and a very interesting and strange moon because we knew it had a dark side and a light side, and we wondered what is the force that creates the dichotomy between dark and light. This was first observed back in the 17th century when Cassini and Huygens realized that this moon seems to darken and brighten. And when Voyager saw it, they saw very distinct boundaries between dark and light. Well, we had two flybys of Iapetus. The first one in 2004, and look at the detail we were able to get. This huge crater. Here we're right on the boundary between the light and the dark areas. There were two theories. Either the dark material was exuded out from the interior, or it was being spray painted from the outside from dust landing on the moon. But why did it only land on one side and not the other? That was the question. Well, they pretty much determined quickly that the spray paint theory is best because it has feathered edges, and you wouldn't expect that from material exuding from the interior. But we also discovered this. What on earth is going on there? Here you see a ridge going right around the equator of Iapetus, and this ridge is 12 miles high. It's a range of mountains right there on the equator. It gives the appearance of a walnut or two hemispheres that are screwed together. So that was surprising. And look at the detail on this crater here. We have a landslide. This crater is 75 miles across. It's within another bigger crater. And then you have a cliff where material fell and flowed halfway across the 75-mile crater. Imagine standing there and jumping off, and you'd be in free fall for a long time. So anyway, what is the secret of Iapetus' dark and light sides? Well, we didn't know for sure yet, but now we had a super close flyby 3 years later. First one was from 77,000 miles away, now less than 1,000. Don't miss this. Okay, now we're coming in for closest approach. And you can see that whatever this dark material is, it must be pretty thin because landslides or meteors can punch right through it and show the bright ice underneath. And here's the mountain range. We're flying right along it. You want to get a little closer? Here we go. Wow. Mountain range with craters on it. And now we're getting to the boundary between dark and light, and you can see some very distinct boundaries, which was quite puzzling. And as we get into the light area, you see more distinct boundaries. In fact, in some places, look at the resolution here, you see dark material piling up against the walls of the white area. So what's going on here? Well, they finally came up with a theory that seems to match the evidence. And what they think is happening is a runaway migration of the dark material. The dark material warms up more than the bright material. And so as it warms up, it begins to move. And molecules of dark material and particles and dust, they start bouncing. And they say, where can I go? Let me go to a cold trap. So they try to migrate to where it's colder, and the dark area gets smaller and the bright area gets brighter. And so you get this process that's a runaway migration. But the interesting thing to us as creationists is that some of this material, as it's migrating, is actually escaping to space as well, about 12% of it, as I recall. And so over billions of years, how much material was lost from this process? All right, here's a global portrait about Iapetus, the dark side and the bright side. You see the ridge of mountains on the dark side, but not as much on the bright side. It sort of peters out on the bright side. We also took a beautiful portrait of Saturn from this distance, which is way out of way. And if you look carefully, you can see 6 moons in the picture with Saturn. And to help you out a little bit, I'll label them for you. There's Dione, Enceladus creating its E-ring, Mimas, Rhea, Tethys, and Titan. Look how small Titan looks from this distance. So that was a famous image. Ring moons real quickly. There are moons that shepherd the rings and even moons embedded in the rings. Here's the F ring we talked about earlier. This is called the Keeler Gap, and it has a little moon called Daphnis inside. Let's take a look at it. There you see a little Daphnis, and it's setting up some waves, some turbulence there on both sides of the gap. And so the equinox observations we made in 2009 were when the sun was right on the ring plane, and to see how thin the shadow is at equinox. And at that time, you can make interesting observations because any objects out of plane of the rings are going to cast a shadow. So we found these things called propellers, like here. And this is Newtonian physics again, where the inside and the outside are moving at different speeds. And so the dust from the interaction spreads out into a propeller shape. And they cast shadows like this one over here. So the estimated size of that little propeller is about half a mile across. And so we discovered several of these, but not as many as they expected. That shadow is 220 miles long on the right side. Interesting. And also on the edge of the A ring, you get motion caused by moons, lofts some particles up and down. And so those particles are going to cast shadows. Look at this line of shadows from particles, parts of the ring that are lofted up above the edge by gravity. That's the B ring edge, I'm sorry, in the Cassini division. The particles get lofted as high as 1.6 miles. Remember that paper thin ring plane? Well, some of them get moved up a little bit more. The prime mission ended in 2008. The equinox mission began that year and lasted 2 years. And then the solstice mission began after that. So we made tremendous discoveries in the main mission and the equinox mission, observed the equinox, 6 more close-ups of Enceladus, flybys of more moons, 28 more Titan flybys, collecting more radar maps and data. So here's the Cassini mission overview. The prime mission lasted 4 years. I was there all that time. Here's the equinox with the ring plane in line. And the equinox mission was about 2.5 years. So at the, but equinox was ending and summer was coming. So they had a second extended mission to explore the solstice mission. And that was going to add 7 more years, almost 7 more years to the mission, from equinox all the way out to the rings opening up again. Look how many more Titan flybys, more Enceladus flybys, other moons, and just all kinds of interesting things to explore. Since the spacecraft is still working, hey, let's use it. It's a big investment out there. At the 10-year mark, I made this chart for the system administrators with pictures of us at various things. You can see my timeline. Longevity on the team was the longest. The next closest one was this guy. Next one was this guy, but a lot of other administrators came and went while I was team lead and so I had the longest tenure of any of the system administrators. Here's a picture of our server room with some of my team. And we had a lot of work, had to know a lot of things about routers and servers and networks, but it was a lot of fun. Here's some of the team and the system administrators on Cassini and on other teams. And this was my group supervisor. And here was one of the pictures I took of me shortly before I was laid off. I was laid off totally by surprise, but we had already issued the lawsuit, so I knew I was hanging under a shadow and not knowing what was going to happen. Okay, the ending of the mission was very exciting because they decided that they were going to incline the orbits to almost perpendicular and then dive the spacecraft through the rings. And the final few orbits would go between the D ring and Saturn. And they didn't know what was in there. I mean, small particles could have hit the ship and destroyed it at that speed. But they decided to chance it because they had already made so many discoveries, and this would be a great way to look straight down on the rings and make observations that couldn't be made any other way. So this was the grand finale orbits that occurred after I was gone, but I watched with great interest.
Well, the Cassini team considers itself a family, a team that works together and plays together. And here is one example. The Cassini virtual singers, they have a knack for putting a Cassini spin on just about any show tune.
So I was watching these things from home, and I noticed with the singers there that they were singing with a track that I had produced and still using it and still going on. And they had a new member, this lady here named Margaret. She was my accuser that pushed the domino that started all the trouble for me. And in the trial, it was determined that by an expert witness that I probably lost $850,000 of lost income and benefits by being fired. And, you know, close to $1 million it cost me to challenge the system because of what had happened. You know, and I don't blame Margaret. You know, she was a nice lady. We got along great, but somehow she went to my boss and said she felt harassed by the DVD about intelligent design. She didn't tell me, she just left the DVD on my desk, but went to him and said that David's harassing me with this religious material. And my boss just chewed me out, and from there it was all downhill. So I'm making about 1/5 of earned income of what I made at JPL. But, you know, God compensates, like I said, in other ways. And I got a surprise email a few years after all this trouble. And look what her sister wrote me. It so encouraged me to find that the Lord had placed people in her path, that Margaret no doubt complained only because she was affected by watching the video, and that scared her. And that our prayers for them are being heard. Praise God. So thank you for sharing the truth with her. It was the right thing to do, and that is rarely rewarded on this side. I tell you, I was really touched by that. She continued, I'm so sorry that you paid the cost that you did, but I'm fully convinced that if you even brought one soul into the kingdom, you will never regret the cost. And I say, amen. So pray for Margaret, and pray for Scott, and pray for Carmen, and pray for my group supervisor, Cab, and many others who watched all this occur. And I hope that my attitude and my actions will be a testimony to them and to others that heard about this story. Well, the grand finale, here are some of the final images, and then we'll end with a video of what happened to the spacecraft. Beautiful images looking down on the rings, looking down on Titan, great detail on the rings, the final images, and then here's the final video.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1.
Here's the launch.
Liftoff of the Cassini spacecraft on a million-mile
Beautiful.
trek to Saturn. We have cleared the tower. Which program is in? What program is in?
Phoebe.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
Around to the SOI burn attitude or pointing position and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system.
Huygens arrival on Saturn's moon Titan.
For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
Well, Cassini is history, but all of its data and images are safely on the Earth. And you know, I think creation scientists ought to take advantage of that data and those images and all that was learned on this great mission and show that the data, the evidence supports the Bible's account of how things came to be. Thank you very much. We've gone a long time, and I'll turn this over to Ross again. I appreciate your watching.
This is the Jacobs family. We're wondering if you could re-explain the moon that had the white side and the dark side, or the light side and the dark side. You said that it looked like the dark pieces were going to where it was cold, but then the lighter side was getting lighter, I think. So where is the coldest part? We missed that. Where is the black part, black stuff going?
Actually, I hope I got that right. But basically, you have this runaway process that's segregating the dark and the light material. And so the ice is collecting, actually the ice is moving, the white ice is moving to the poles and to wherever it's not getting the most sunlight. And so that's the kind of migration that's happening. But it's been a while since I read about that. I hope I didn't mislead anyone, but the basic idea is that it's separating out into dark and light areas. And that finally, we think, explains the dark and light sides. Nice to see your family.
Thanks for clarifying it. Yeah,
nice to see your family joining. Thanks for watching.
Thank you.
Yeah, you're welcome. My 8-year-old just said, "Wow, Mom, I learned so much tonight." So that's awesome. This is our science
That's great.
class tonight.
Good science exercise, yes.
Yeah.
Very good.
Thank you all for watching. Who's next?
Were the Ridge Mountains ever figured out on the equator of the moon?
You know, Iapetus, that 12-mile high ridge, I don't think they really have an answer. I've heard a couple of theories. One is that at some point in the past, the moon was spinning so fast that it sort of bulged out, but you wouldn't expect a narrow ridge to extrude like that, would you? In fact, I should look at the camera. You shouldn't expect a narrow ridge to extrude like that. You would expect more of a wider thing. Another idea is that Iapetus may have had a ring, and that's collapsed material, but that's a lot of material to collapse from a ring. So they don't really have a good idea. It's a mystery. Maybe creation scientists could look into it.
Could it be a close flyby of another massive body that circled it and warped the crust?
Could it be a close flyby? Well, I suppose so. There's no good hypothesis right now. So let's come up with some and test them against the data that we have. And that would be a good exercise for creation scientists.
Yeah, David, thank you very much for this. It's going to take a while to digest this, and this is going to go on. It's going to go on YouTube, and so it can be viewed repeatedly. I think we're going to get lots of viewers. My wife and I watched the television special on Netflix of the last flight of the Challenger, which deals with O-rings and plumes with a different spin on it. And I think the spin was the spin that we saw among NASA scientists who had trouble with the truth. And I think you saw the same thing with the Jet Propulsion Laboratory scientists. There's problems with the truth, and especially if people are feeling conviction.
Well, I would not criticize any of the people that I know as being intentionally like that. It's just that it's so ingrained in our education system that everything is billions of years old. And there's just not enough people willing to think outside the box. And I've heard scientists say that, wow, there's an upper limit of 100 million years on the atmosphere of Titan, or how can Enceladus be pumping out this material for billions of years? And they raise the question, but they never question the assumption of the age of the solar system. I call it sort of the law of the misdeeds and perversions that cannot be altered, you know. And so, yeah, people just cannot think outside of the box. And one of the consequences of reducing the age of Saturn and these other objects is that it doesn't leave enough time for Darwin, you see. And that's one of the perverse incentives to keep things old. But they don't really have good answers. They put forward ideas and theories, and I read them. But it's almost like they have to invoke miracles. For instance, to get the rings. One theory that somebody put up, Dr. Canup, thought that, well, maybe a Titan-sized moon wandered into the Roche limit around Saturn and busted up and became the rings. Well, that's a convenient theory. It's almost impossible to test because we've never seen that happen anywhere else. And it's a historical thing, not an observational thing. But the probability of getting a body that big to pass by that closely at just the right time and speed for that to happen it's like believing in a miracle, basically. So when you're dealing with the origins of things, you have to realize that we weren't there either. We don't have the observations, but we can say, well, which hypothesis of age better fits what we do know and what we do see. And believe me, it's easier to set an upper limit like 100 million years than it is a lower limit like, oh, well, billions of years. Because with an upper limit, you can say, all right, well, we've observed maybe this much, and we could go extrapolate a little ways out, but not a long ways out. And so when they say there's an upper limit of 100 million years, on some of these things, they put upper limits of 10 million years. Now, remember my rope illustration? 1 foot is 100 million years on this 45-foot rope. Well, how much is 10 million years? It's 1/10 of that 1 foot. You're getting down into just micrometers almost. The more you get down, the upper limit gets lower. And so that's the problem, that you don't have the time you think you have to produce these phenomena. And this is a golden opportunity for scientists who think outside the box and don't buy the materialist assumptions of billions of years to come up with hypotheses of about Enceladus and about Titan and about its atmosphere and about Iapetus So I hope this will stimulate scientists outside the box to put some new creative hypotheses and tests together.
And all that data can be gotten? The data is available?
Yeah, if you go to the nasa.gov site and search on Cassini, I'm sure they have repositories. Some of the data may be the property of instrument teams. One of the things I did was help provide the computer and network services for about a dozen instrument teams across America, University of Colorado, Imperial College London, in France, and so I would communicate with them with their software and computers, but they may have the proprietary rights on some of the specific data. I don't know the status of that, but I'm sure it's publicly available because this was paid for by taxpayers, basically, and so it's public domain information.
Say, David, I have one question.
Mm-hmm.
They're saying they think that there's oceans of hydrocarbons. Where are these how did these hydrocarbons form? Here on Earth, they said that our pools of oil is because of decaying dinosaurs, and I was just wondering, how did those hydrocarbons form to that quantity?
Mm-hmm. Well, I don't think they have dinosaurs on Titan or fossil fuels or anything, but methane is not that uncommon a material in the solar system. It's found around other planets and places. And not all of the methane on Earth may be from fossils, dinosaurs and things. There are processes. I'm not a geochemist, so I can't speak with authority on these things, but there's a process called serpentinization I've read about, where methane can be formed from rock material under certain conditions. And so methane CH4, it's a simple molecule. And I'm not sure how it got to Titan. They think, well, maybe there were methane clathrates under the crust that somehow erupted out through cryovolcanoes. But you know, how do you get some kind of cycle that will make it go down and back up and down and back up? And especially if you have a lot of it being reformed into ethane, which will not recycle. It's just a liquid at Titan temperatures, and it should just remain on the surface and not evaporate and not go back up. So these are good questions. I'm not sure how the methane got there, but it is there. I think they find some methane in the clouds of Saturn and other parts of the Saturn system. So good questions, though.
Thanks.
David, I have another question. Enceladus is such a small moon or a body of the four active, geologically active bodies. Are there any studies that talk about out in space, if you have something like the size of a school bus that is molten hot, how long would that become the ambient temperature of space? Or, you know, I mean, you know, gradations of size. I mean, Enceladus, you know, I mean, a scientist must say, you know, it's still geologically active, so it can't have been there that long. Is there any limits on that?
Yeah, great questions. And I think that the burden of proof is on the materialists who believe in millions of years and billions of years to prove that that activity has gone on. Now, what they try to invoke is tidal heating. Like if you squeeze a rubber ball repeatedly, it heats up, right? And so if they can get tidal heating on Enceladus so that it keeps pumping and pumping, it may keep the ocean under the crust liquid and allow this to go on. But when you do the math, I think you would find that Enceladus should have recycled its entire interior multiple times over billions of years.
Exactly.
I know that's been said about Io, that Io has produced so much lava out of its interior, and these are heavy lavas too that should have sunk to the interior, but they keep getting erupted out these vents that Io could have Don't quote me on this, but I've heard that Io could have recycled itself 45 times over by now, if it's as old as they say.
Wow.
So yeah, these are great problems for billions of years, I think, that deserve further study. You're welcome.
Oops. Can you hear me?
Could you explain how there can be a communications path between a station on Earth and that controls and transmits data to that Cassini, and it happens, and it follows billion. It's traveling a little signal is traveling millions of miles back and forth. Does the path is kept open by the signal so that it never loses its target? In other words, you're millions of miles apart. They're both the Earth and Saturn are moving in different directions, and you can't predict where they're going to be if you start out a signal.
Yeah, those are good questions. And this is a big subject about the Deep Space Network. By the way, Dr. Henry Richter, who I mentioned at the beginning, the co-author of my book, also worked heavily on the Deep Space Network development, including picking the sites. There are basically 3 Deep Space Network or DSN stations around the world, so that any one of them can be pointed at a spacecraft as the Earth rotates. One's in Spain, one's in Australia, and one's in the Goldstone Tracking Station near Barstow, California. I visited that one a couple of times. But they have these big dishes, and they're not only monitoring things like Cassini, but many spacecraft. And so you have to there are engineers who have to plan out what time slice each spacecraft is going to get to transmit. Plus you have the speed of light difference out at Saturn. I forget, it's around an hour and a half travel time from the time the signal is sent to the time it's received on the Earth. So yeah, it's allotted according to a very detailed timeline, and there's interruptions like, oh, we're making this great observation, we really need to, and we have this one opportunity to get it, so can you point the antenna at us? And the antenna has to be pointed at the spacecraft. The spacecraft has to have its high gain antenna pointed at the Earth. And these things have to be very, very coordinated. So it's a highly complex process, and I'm amazed that they actually get it to work.
Thank you.
By the way, the energy of those packets, those 1s and 0 bits that travel in pulses through space, is less than the energy of one snowflake falling to the ground. So it's amazing that they can pick up that data. And of course, there's a certain transmission rate. So you have to collect these bits over periods of time. It's packetized into predetermined formats with headers and everything. So that's a really amazing system. And it works. I mean, talk about intelligent design of the human mind. That's an amazing thing.
Hi, my name is Brad. I used to go to a Bible study at the home in Pittsburgh, Pennsylvania, of Terry Rockwell, Willard F. Rockwell III. They're the corporation that built the space shuttle. So I would mention his name to you. I think he's probably still alive. He's probably in his mid 60s or maybe 67, 68, but Willard F. Rockwell III, he's a born again Christian. He was on the board of, he had a security clearance with NASA, and he worked with some NASA spinoffs, but I think he was on the board of Regent University, a Christian Broadcasting Network. It might be a good connection for you, someone to network with. And, you know, probably, his nickname is Terry, Terry, but it's actually Willard F. Rockwell III. The last I heard, he was living in Pittsburgh, Pennsylvania. Probably someone in the Christian community there, or somebody through Christian Broadcasting Network could put you in touch with him. But the grandfather of the founder of the Rockwell Corporation that built the space shuttle. And so I think, and again, very, very serious born again Christian, and I think he'd take an interest in your program there. And also, just one last thing, I think in a situation like the injustice that you suffered, usually it's a better thing to, have a trial in front of some ordinary people, like a jurors, 12 jurors instead of one judge. The judge, is an elected official, and whoever contributes to the judge, his re-election campaign a lot of times can have some influence. So, and jurors, they probably wouldn't even have wanted to try this case in front of 12 jurors. They probably would have settled. But I don't know. You made the decision for some reason back then. But I would just add that as a comment. Before the ordinary folk on the jury, I've heard over and over that that's often a better thing. 12 people.
I know Dr. Jerry Bergman would have preferred that too, but you face actualities in practice that we were facing rising costs. I mean, it costs a lot of money to put on a trial, and even though we had Alliance Defending Freedom helping us with some funds, we didn't have enough, and the cost just kept piling up. And we were told that if you have a jury trial, you got to pay their salaries for coming, and that was going to pile up way more than we could afford. So we hoped on the judgment of a judge that was supposed to be an expert in employment law, but he was appointed by a liberal California governor years ago. And later we found out he got into trouble with the legal profession himself for laziness and turning over all of his work to his staff and being late to trials and stuff, which we noticed during our trial. So we had to just roll the die on just one chance, one judge. And I'm certain he didn't, in the cocktail lounges, he probably didn't want to be known as the judge who supported intelligent design. So who knows?
Right. And they just say, I've talked to many lawyers, and they say, even if you have 100% airtight case, you can still lose your case.
Yeah, I learned a lot about the legal.
We're in a fallen world, and it's not as perfect of a judicial system as we're led to believe when we're kids. So
I know. I learned a lot about the legal system that was sort of not very comfortable or encouraging to learn, and just the tricks that are played. And of course, this was a huge David and Goliath contest. And who was I to think I'm going to take on NASA, a single whistleblower here? They had all the best lawyers, the most money. Their legal team has a skyscraper in downtown Los Angeles with their name at the top of it. They have branches in Rio de Janeiro and Hong Kong and Paris and London. And I had one lawyer from ADF taking on this monstrous thing.
Just look at this website, Divorce Corp, CORP.org. And that'll tell you a lot about our legal system and how it compares to other countries. No, that's a good one. See that. Check it out sometime.
Well,
but thank you very much.
Well, look at Jerry Bergman's trilogy, Slaughter of the Dissonance. You'll read some really
I think
shocking stories.
Thank you.
Maybe one more question, and then we're going to have to tie it up. Is there one more? Well, I'll make this comment. The final answer is that God is on the throne. And I think you got a little glimpse of what God is doing as a result of this.
And in spite of the trial, God has been good and faithful as he promised. I learned a great deal, and I hope that my experience inspired others. We have to take a stand. We can't just let evil swarm over us. And we don't always win if we take a stand. And I didn't legally, but I think I won in other ways. And I just hope the Lord found me faithful in this incident.